Okay, thank you so much to the 3D Metabolism team for that amazing presentation. So next up, we have Oer Geomatics. So the project team includes Juno Yoon and Floria Gu. So before we hear from the students, I'll just pass it over to PI Dr. Paul Piquel to say a few words.
Hello, everybody. My name is Dr. Paul Piquel. I'm an assistant professor of teaching in the Faculty of Forestry, and I teach geomatics, which is the art, science, and technology of collecting and analyzing data and information about Earth. So quite a big topic, and the project that I'm going to introduce is this OER Geomatics textbook that we're working on. So OER is an acronym for the Open Educational Resources. So this would be an open and freely accessible textbook that we're trying to achieve here. So probably about 5 years ago, I dropped my initial paid textbook from my classrooms because I was really dissatisfied with the cost and a lot of the existing content that's out there is very American-centric, and I'm an American, so I feel like I could say that. So a lot of content maps and stuff are oriented towards American problems, the United States context, and there's not a lot of really good content out there that's open and available for Canada. And as well, despite some of these online textbooks, and these are examples from two, the one on the right here, both of them, are just using very flat images, very two-dimensional images, despite being hosted online, which I thought was really, really disappointing. So my colleague and I, Evan Thornberry, who's the GIS librarian here at UBC, we set out to develop our own new textbook. We got funding through the OER implementation grant here from UBC to do that. And we started doing some of our own stuff, like creating just some simple web maps and other interactive content that we could get by on. And we recruited a bunch of graduate students to sort of help us get to that stage. But admittedly, it was still quite two-dimensional, and so this was the reason why we reached out to the Emerging Media Lab to help us work on some of those interactive elements and really take advantage of the full potential of that online user browser experience beyond just web maps and other kind of visualizations that we could do on our own. So with that, I will hand it over to Juno and Floria to introduce the great work that they've just been working on.
Thank you, Paul. So before we begin, our team consisted of our principal investigator, Dr. Paul Piquel, Evan Thornberry, and for our EML side, we had project lead as Juno Yoon, and staff developer as Dante Saren, and software developer as Juno Yoon, Floria Gu, and Kenny Zhao. And I'll pass on to Floria for the introduction.
Thank you, Juno. So this past term, our team created interactive visualizations to support 2 chapters of the textbook. The geodesy visualization for chapter 2, mapping data, and the LiDAR visualization for chapter 15, LiDAR acquisition and analysis. A third visualization about the electromagnetic spectrum is also in ongoing development.
Thank you, Floria. So the main technologies that we used were React 3 Fiber and 3JS, which are used to create a online 3D content in the browser environment. We also additionally used Leva Control right here, which provided a intuitive side panel for the user to be interacting with the visualization. Additionally, for hosting our visualization, we used Amazon S3 Bucket, which is used to create a temporary link where the user can just click on it and access the visualization. This was used for internal testing as well as user testing. Now I'll pass on to Floria for the geodesy visualization.
Thank you, Juno. Yeah, so this term, I worked on the geodesy visualization. Geodesy is the science of measuring the shape, orientation, and gravity of Earth. One important task that students must learn is how to specify the height and location of points on Earth. So the coordinate systems that we use are actually anchored against reference surfaces, which are models that approximate the surface of the Earth. These models could be as simple as a sphere or as complicated as the geoid. And understanding the coordinate system is important because using the same coordinates could put you in two different places if you happen to use different coordinate systems. Now, since these reference surfaces are inherently in 3D, we thought that an interactive tool could provide a fuller appreciation of their differences than existing flat diagrams. So for this chapter, we created a 3D visualization around three models of Earth's shape: the sphere, the ellipsoid, and the geoid. Our goal for the geodesy visualization was to enable the students to explore the models in 3D to better understand their differences for referencing height and location on Earth. We also wanted to create a tool that instructors could use in class to guide discussions and encourage active learning. The primary features of the visualization are these 3D sphere, ellipsoid, and geoid models, which can be shown or hidden to compare against one another. Since the geoid surface is an irregular surface, we used a public data set of geoid heights to create this 3D model in Blender. Also, we added supporting 3D geometries, such as lines and points, to show how the latitude and longitude coordinates would interact with the three reference models. And lastly, the geoid height view is a restricted view that we implemented to visualize a specific concept in the textbook called the geoid height, which compares two of the models specifically, the ellipsoid and the geoid. Yeah, so in January, we tested this prototype with 5 students from the textbook's target audience. The students expressed that they needed more context to identify the models and connect them to the height differences that they were seeing, so we added legends. Also, it was important for us that the users are able to access the textbook from many different devices. For example, they could be using their phones during an in-class activity, which is why we created a responsive layout that is able to adapt to mobile screens. Okay, that's it for the geodesy visualization. Now I'll pass things over to Juno to talk about the LiDAR visualization.
Thank you, Florio. So before I go into technical details about the LiDAR visualization, I'd like to provide some background information about what LiDAR actually is. So LiDAR stands for Light Detection and Ranging Technology. For geography concept, LiDAR sensor is mounted to an aerial vehicle like this, which travels across the Earth's surface, and it emits a laser pulse and light signal. And the signal is then reflected and collected by the same sensor. This records the approximate XYZ coordinates and additional attributes depending on the setting of the sensor. The collected point cloud data is then used by the feature manipulation engine to process the data to a point cloud data. Once the data has been processed, that data could be used to create some visualizations. So the following are some example of visualizations written by the point cloud data. So the typical point cloud data like this, and right over here, consists of the XYZ coordinates, the intensity and elevation level, along with the number of points and the size of the points. So these two visualizations are the same visualizations. However, the one at the bottom does have a thicker density of points. Additionally, some visualizations here, you could see that they are different colors. So the one at the bottom represents the intensity in RGB. The one at the top right represents intensity in black and white. And one on the left, top left, represents the elevation level in color. So to write such a visualization, it proposed several challenges. Number one was determining a way to process the point cloud data. Because the point cloud data came in a lot of different data formats, such as LAS, LAZ, and EPT, it also proved to be difficult to figure out exactly which format that we should be using. Additionally, as the visualization has a number of different customization abilities, such as allocating number of point budgets and allocating intensity color, those algorithms also had to be developed as well. And lastly, the controls involving camera in 3D environment proved to be challenging. To overcome such issues, we also reached out to another open source library called Pottery WebGL Point Cloud Viewer. This application is able to process widely accepted point cloud data formats and has several built-in functionalities, such as classifying different parts of the point cloud, determining a method to allocate elevation level depending on the XYZ coordinates, and other customizable features such as camera controls and, different visualization view. So we converted our Pottery application to a React application. This provided a way for user to access the visualization without running a server on their end. Additionally, we implemented query parameters to enable the students to reach out to the visualization in exact format they require. As this visualization is to be used in a textbook format, the instructor could customize the URL with the exact parameters that they would like, and the visualization would be loaded in such format. By doing this, we made sure that the visualizations were interactive, intuitive, and ease of use. Additionally, our original prototype did not have a way for the user to manually change the visualization and the classification without the use of query parameters. However, after the user test, the users advocated a need for built-in controls, which we implemented using Leva control. Additionally, we also implemented a way for query parameters to disable the built-in controls so that the user would not be distracted from the primary purpose of the referencing from the textbook. This concludes our presentation for Oer Geomatics, and thank you for listening to our presentation.